Swayam Prabha. Digital India. Educated India.
Welcome back to the lecture series in annual physiology. So, we are into the 5th lecture of the 11th week. So, we ended up at turbulence, right. If you remember, I told you that if the surface becomes uneven, if the flow all of a sudden changes its rate, there is a higher flow, and on an uneven surface, this may lead to very unusual motion of the blood at vessels, and that may lead to hemorrhage, that may lead to rupture of the vessels. Several complications may arise due to that process. So, from there, from the turbulence, that is where we stopped. So, once again, give me a second. Okay. Now, let me continue here with our week 11, lecture 5. W11 L5. Okay. So, now continuing upon it, our next definition which is important will be vascular resistance. What is vascular resistance? So, the vascular resistance is a resistance due to friction within blood vessel, due to friction within a blood vessel, primarily between the blood and the vessel wall, primarily between the blood and the vessel wall, between the blood and the vessel wall. Increase this, so now which increases. So, the vascular resistance, I am just indicating as vascular resistance increases with increasing length or decreasing diameter, with increasing length or decreasing diameter of the vessel. Okay. Now, vessel length is constant, but the vessel diameter can change. But this one is your constant parameter, whereas this diameter, and we have talked about what are the different situations where diameter can change out here. Look at it. So, if this is the original diameter, so because of the deposition which is happening on the surface, some form of deposition like this, something like this. So, your diameter is changing. This change in diameter influences the vascular resistance, whereas your length is constant. Okay. So, you cannot really change the length. So, this one is the changing parameter. Okay. And this one is a constant parameter. So, keep these in mind. We may have values, we may have but then you are the best judge to understand that which parameter can be changed and which parameter cannot be changed. Okay. So, now we have few more definitions to deal with. Should be dealing, just let me add few more pages into it. Coming back to the next definition, which is your venous pressure, the pressure in the veins. We talked about arterial pressure, now we will talk about the venous pressure. So, venous pressure is the hydrostatic pressure in the veins of the system. Hydrostatic pressure in the veins of the system. Then comes your viscosity. We have already discussed it. Resistance to the flow due to interaction among molecules within a liquid. Due to, this is very important, keep an eye on that, due to interaction between the molecules, or you can call it even particles, in the case since we are dealing with cells, particles within a liquid. Within a liquid. So, just do not go by the drab definition of it, think over it. Say for example, the blood is flowing, it has a certain, I discussed about this, it has a certain viscosity because it is a fluid on which there are particles of proteins and other molecules, biomolecules which are suspended. Apart from it, there have macro particles in the form of cells, red blood cells, white blood cells, platelets. So, if you look at blood as per se, then you have one hand you have water, which is the base, plus, so this is the fluid part of it, then you have WBC, RBC, which is the highest number, actually I should have RBC, then you have platelets, then, so these are macro particles which are present there, then you have the micro and a nanoparticle in the form of proteins, albumin and likewise. So, now say for example, try to understand this, say for example, because of fever or something you are undergoing, the number of, say, so now if say for example, this WBC number goes up because you have some form of fever or something, your body is fighting. So, automatically what will happen, this viscosity parameter, viscosity of the blood is going to go up. So, automatically if the viscosity goes up, because now there will be interaction among the particles, they have to move, like they are moving like this, fine. If there is a more of a friction among the particles, then the movement will become slower. If it becomes slower, so automatically the viscosity has gone up. Now, in order to pump that much amount of blood from point A to point B, there is a finite time t. Okay. Now, if the viscosity goes up, that will be taking, that time will be time plus delta t. There will be more time which it will be needing. Now, that may damage your system. Okay. So, in order to compensate for that, the heart has to, or the pump has to work at a faster rate. So, now if the pump is working at a faster rate, now you remember the definition, that now you have the turbulence and all those kind of things which are going to pick up. So, it is very essential that you look at this whole picture in a complete totality, and that is why I am putting down all these definitions and think through these definitions. These definitions are not just drab definitions. Okay, these are definitions with certain meaning, which should provoke you to think over it, that what does that mean? The viscosity increases, and there are drugs which people take, especially sports enhancing drugs, which increases the viscosity of the blood. It makes the blood thicker. and because of the thickening of the blood, at times these sportsmen suffer from cardiac arrest. It does happen. So, you have to look at your body in its complete totality, that what all possibilities can emerge out of it while it is functioning as a unit. Okay. So, please keep a very close tab on these definitions. Okay. Now, coming to the next definition in that line is our, so we have done with the viscosity. Now, we will talk about the relationship among these terms. This will be very critical. So, put all your attention about it. A relationship among these terms. Okay. So, the force is directly proportional to the pressure difference, that we know. If the higher pressure, it will move from higher to lower pressure. So, automatically at a higher pressure, the force will be more. Relation 1. So, which is, sorry, mistake. So, basically your flow in this case is proportional to the pressure gradient from higher to lower pressure. Now, next relation, flow is proportional to 1 upon R, which means flow is inversely proportional to resistance. Inversely proportional to resistance. 3. Flow delta P upon R, that means flow is directly proportional to pressure gradient and inversely proportional to resistance. If you add these two, okay, this is what you are getting. Flow is directly proportional to pressure gradient, but inversely proportional to resistance. Next, flow has a relation with Vp/PR. Flow is directly proportional to blood pressure and inversely proportional to peripheral resistance. Similarly, the last of this relation is resistance is, so resistance is inversely proportional to the fourth power of the vessel radius. Having said these relations, I will come to the relationship among the next set of relationship, which will be more of a graphical one. A relationship among vessel diameter cross sectional area blood pressure and blood velocity. Let's draw the relations. The first relation we are talking about is vessel diameter. If you look at the vessel diameter, you will realize if this is your elastic arteries EA, this is your muscular arteries, this is your arterioles, this is your capillaries, this is your venules, then you have the veins, venules, veins, and this is the vena cava. So, we will kind of keep this tab intact because we will have to repeat this. Okay. 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 Now, if you see in terms of the vessel diameter, so the vessel diameter is the way it changes. So, these are in centimeters, okay, vessel diameter. So, approximately 2.5 centimeter where iota is. Iota is around, this is around 2.5, okay. So, this is, if this is 2.5, this is say 1, 2, 1, 2, 3, this is the 2.5. So, the way vessel diameter changes is as it goes down, it comes to the arteriole, capillaries, and then the vessel diameter from here increases very sharply and goes up like this. So, you are realizing the vessel diameter changes in a big way out here. This is the comparison you have to kind of engraved in your brain. Next, in terms of total cross sectional area, total cross sectional area. If you look at the total cross sectional area, so the cross sectional area is very interestingly varying. So, out here it is perfectly fine, and from here it started to increase and it becomes maximum at the capillaries, and then it starts to fall down. It will be always slightly, so you can use another color for this side, kind of give you the feel. So, if you look at this area, this is the area where you have the maximum total cross sectional area, and if you look at the values in terms of the numbers, if you look at it, this will be around 5,000 centimeter square, okay, and out here possibly. So, if this is 5,000, you just 4,000, 3,000, 2,000, 1,000, 2, 3, 4. Okay. This is the cross sectional area we talk about. Now, in terms of millimeter mercury, if you look at it, the way the pressure changes, so if this is 100, the way the pressure changes is something like this. This is the highest, 100 millimeter mercury down, and by the time it reaches the capillaries, and then that's it. So, here you are having the maximum, reducing, further reducing, and then is a slight increase, that is because of the valves which are ensuring, and there is a squeezing from the lymphatic vessels and all. So, the average blood pressure you can calculate from this. So, this is your average blood pressure. Okay. Now, the next and the last of these relations is out here. Velocity of the blood flow, which by this time you should be able to predict it. Velocity of the blood flow. So, the velocity of the blood flow kind of in terms of centimeter per second, if you look at it around, like, if I say this is 30, so 30 centimeter per second. So, if this goes, so this will fall down like this, and there will be slight increase, but not a whole lot. So, if you look at it, the maximum velocity, so if this is 7, this is 14, this is 21, this is 28, this is around 35. So, if you look at it, is the velocity is maximum out here, it is reducing, it is reducing, it is reducing, and then there is a slight increase out here. So, this is the overall arterial blood pressure, and mean arterial pressure, which is called MAP, mean arterial pressure. Sometime in the books you will see it is called as MAP. Mean arterial pressure is equal to diastolic pressure plus pulse pressure divided by 3. This is how the mean arterial pressure is being calculated. Okay. So, having said this, you must have a fairly good idea how the vessel diameter and vessel architecture kind of influences all these different parameters, and this is where the peripheral exchange is taking place. This is where you have the exchange taking place in the lungs, and followed by the architecture of the arteries and the veins, and this is how the architecture varies over the period of time, and these are the parameters what we dealt with. So, I will close in here. Thank you for your patience listening. Next week we will start with the endocrine and we will finish off the rest of the course. Okay. Thank you.